Hi everyone, welcome to our project. Our project is project 2116. It's called Parallel Anytime Branch and Bound Algorithm for finding the tree widths of graphs. And I'm going to explain what that is just in just a moment. My project mentor is John Brennan, and my project partner is Valentin Trophime, and he'll explain about his part of the project a little bit later on. So firstly, I'm just going to talk about what the tree width is and how you would go about finding that. So informally, the tree width is basically how far away a graph is from being a tree. So say if you have a graph here, on the right, if I remove one of these edges, then this graph would become a tree. So the tree width would be 1. So remove the edge, it becomes a tree. The tree width can be a useful value to have, and you can have it in different types of algorithms within graphs. For example, you can have it in shortest path algorithms or just searches, and one of the other uses is in quantum computing. So basically, Google used a Treewidth algorithm to validate the chip output of one of their quantum computers. These algorithms can take a long time to process, so they have to be done efficiently. And as you can see here, the order in which some of the contractions are done, they all equate to the same thing, but how these are calculated are very different, and it's important that they're done in the most efficient way. So the part of the project that I've been working on is on an algorithm called QuickBB, which is quick branch bound, and essentially what that does is it's a DFS algorithm, and it computes the upper bound of the graph, the upper bound tree width, and the idea is that I end up parallelizing it to make it faster and more efficient. So the way that this works is we start off with a tree width of 0, and then we look at the very first node, so we select that, and then we see how many neighbors it's got. So in this case it has 2 neighbors, and then we interconnect those neighbors. So here there's a new connection between 2 and 5, and because we've got 2 neighbors, we put that into the function, so we get max 2, and then we get the tree width, or the previous tree width, which was 0, but then the max of that is 2, so the new tree width is 2. And then we delete the first node, and then we get a graph looking like this. Afterwards we select the second node, and then we do the same process, and then we look at the max function again, and then again it's 2 neighbors, and then the previous tree width, which is 2, and then again that remains the same, so it's 2, and then once again we delete the second node, and then we're left with a graph like this. And then select the third node, again same process. Select the fourth node, again same process, except this has 1 edge, and then this is put into the function, and we stick with the max, which was 2, and then we delete that node, and then we get the 5th, and it's selected, and then 0 connections. So that's it. Here's another example of the elimination order. I don't have time to go through it now, but feel free to pause the video to look through it yourself. So going back to QuickBB again, we learned that it's recursive DFS search that computes the upper bound of the graph, and in order to do that, we have to store the orderings, and we have to form an order to find the orderings with the lowest tree width, and we do this for every single node in the graph, so it's done in a brute force manner, and because of that it doesn't scale very well, and the way that we can speed this up is we can run it in parallel. It's also important to note that the orderings does matter, so it's hard to find the best case scenario. So the way that we can order it is we can shuffle it, and we can just randomize the shuffles, and we can use MPI to shuffle the orderings of every branch bound search. So that's pretty much the basic overview of QuickBB getting the tree width of a graph.
Another algorithm to solve the same problem is the flow cutter algorithm. The flow cutter algorithm is simple. It takes a graph as input and returns an order and the Treewidth of the graph. It is made of 3 layers. The first layer, the dissection, is really simple. It only calls the second layer to find the separator and then cuts the graph in two subgraphs with the separator and apply recursively the same strategy on the subgraphs until the subgraphs are complete or are trees where we know the best order for them. And we construct the order by adding the nodes in the separator and the node in the subgraphs when we can compute their order. How do we compute separator? Separator are computed by calling the flow cutter layer with random source and targeted. In practice we do this several times, and then select the best cut. The best cut is the cut with the minimum size and the most balanced cut. And then we choose nodes from the cut arc, the arcs of this cut. In this example we take 7 and 6. So now let's dive in the main part. The flow cutter core. It will require some notion like the flow, which is basically just a number in the graph, a weight on the edges. It represents an amount of water you can put in the pipe, for instance. The pipes have several capacities. You can put more water in it. It also has a source that can create flow and target that can receive flow. All the other nodes have a kind of conservation of flow. It has the same amount of flow in and the same amount of flow out. One classical problem that we can solve in polynomial time is the max flow problem. The idea is you want to put the maximum of water from a source to the target through a network. And this is solvable in polynomial time, as I said, and it is equivalent to another problem to find the minimum cut capacity, and that's why flow cutter returns us cuts. So the main algorithm is taking graph, a source and a target, and compute cuts by solving the maximum flow problem, finding the cut. If the cut is balanced, it stops, but else it will add new nodes as source and target